to the consideration. Basically, the power flow has to happen from the grid side to the 400 volt. So it is acting as a here it is a kind of a controlled rectifier. Power factor correction has also need to be done in this front end side. So this is for the during this positive half cycle, what are all the switches will be operated, and negative side what switch is operated. That's what I have mentioned over here. So the other side, when the negative half cycle, when the power flow is up, the current is in the other direction, that has been marked over here. So basically here the control algorithm, if you see that the battery current in the reference which we are taking it, when based on that S4 and S5 is turned on during the battery charging mode, because the battery current will come into the outer loop where we have to set that the reference and we are charging it. This is the inner loop. Outer loop, if you see that the voltage based on the where we wanted to stop it, according to that sensed voltages, wherever this is the switches which is across the diode in the again bridge side. So if you look at it, you will get it. So this is basically it is for the grid side power correction. If you see that the DC bus voltage is taken and it has been compared and we are getting that the PI value, this is nothing but my power value, how much power I am getting it. So the basically the unity sine waveform, if I do that, so it will give that the PLL is going to sense that sine waveform is the reference which is with respect to the waveform, grid voltage waveform. The PLL will give unity sine waveform which is shared, and it has been multiplied with the factor, the PI controller itself. We are acting as the factor. So it divide the component grid is connected with the unity power factor system, and it is connected with the system, and it is taking care of that power factor, unity power factor. At the same time that the maintaining that 400 voltage of that power, we are taking reference as a voltage 400 volt and pushing the power, and the system is works according to that. So this is another case where that the charging has to happen for that when the grid current reference is taken and the reference is connected with the PLL, where the power factor is unity power factor, we are pushing into that. This is for the vehicle to grid, the current reference will come according to that. In this case, if you want to compensate the reactive power, that is another option we can take it, because normally in the household load, if you look at it, the single phase cases, the induction motor or the motor loads, and some of the loads which presently it is only the load which we think that induction motor is having that the non-unity power factor. So that power factor can be compensated by adding a reactive component of current also with respect to this, and it can be fed that the rated power to the system with the to compensate compensating both the reactive power as well as the power. What we have taken the reference, this is the value 1.5 kilowatt, 48 volt, 200 Ah battery, 230 volt and 50 hertz component. 230 volt, 50 hertz component, it's a input side for the grid. So those things we have taken into the consideration and we have worked according to that. So this will give that that overall system. This will give that overall system value, system rating, and the high frequency transformer is designed for that. You can see that 48 and 480, 480. Even though the DC bus voltage is 400, we have designed it for 480 because of one is the winding losses is going to be there. The another one is the duty cycle is not exactly 50% we are keeping at this particular case. So that is the reason we have taken it into that. All other values we have taken into the consideration. Based on that we have designed. You can see that when the battery is charging the voltage, at the same time we are drawing the voltage, you can see, and what is the time it is settling. 0.2 seconds, it is 0.2 seconds, it is nothing but that in out of 50 cycles, 0.2 seconds it is going to consume the 10 cycle. Within the 10 cycle of my input supply voltage, this is settling over here. Here also you can see that around 25%, the current variation, we can see that the settling is happening at this 0.4. You can see that the input current, how it is in phase with the grid current alone. There is a in phase component. You can see that both are matching with the input power it is drawing. See that the instant where it is the power is transferred from the vehicle to grid. So here the minus going into the discharge mode, and at the same time the DC voltage is also maintained. You can see that the output power which is transferring to the grid in the current waveform is 180° out of phase with the voltage waveform. So this indicates the power flow is happened in the one direction to another direction. At the same time, we have taken care of all the THD and other parameter in this particular case. So the continuous variation is also we have analyzed for system stability point of view. So 20 and actually you can see that the discharge current is more. Normally the battery you can take more current than the charging current. Charge rating according to the C rating we have to control that current. So that is what it has been shown. You can see that the DC bus voltage also. At the same time you can see that the voltage profile, how the current profile, how it is in the complete cases. And we have zoomed this area. You can see that basically the current is here it is the in phase component, here it is the out of phase component. So again from out of phase component to in phase component it is coming. So that means it's a transferring the power and it is absorbing the power. So basically we have done it. This is for the system. It can be worked with 48 volt to 96 volt at the maximum at the DC side. Also it is always it makes the power factor. The aim on this particular one is to make it that the system to be in a constant load line. So that is my aim on this load for this duck curve. The duck curve is coming the normal load profile. If you see in grid, this is what the profile. By adding more EV vehicle, if you are going at home and will worsen this curve so fast. So in the daytime or during the night time, you charge the electric vehicle and discharge it. The main drawback in this particular system is the battery is the charge discharge number of charge and discharge cycle is going to be increased in a day because it is not used for the vehicle, it is to balance the grid we have using it. So that may cause the battery life to come down, and that study need to be done what kind of optimum value we can do so that grid is also not going to get affected and the voltage stability will be good. At the same time the battery life can be estimated. This is the thing is basically it will help the people of battery manufacturer. At the same time the grid reliability where it has to be operated, economic dispatch also will be taken care in this particular system. So this is the system which I am talking about, where the uh, converter is connected to the system and it is pouring the power to the grid, or it is either it is a drawing in the power. The other one application which I wanted to share it here. So basically the bidirectional, it is sorry, bidirectional, it is it is basically it is to be you can see that it is connected with the standalone mode, the electric vehicle, how it is going to be operated grid to vehicle connection. So grid to vehicle charger, the power flow is unidirectional, and bidirectional means the power flow is bidirectional. Excess power can not be harvested here. So basically in this configuration, so this work basically we have done it with the PV based system also into connected into the DC bus. So how it will be connected, if it is a PV is connected into the one direction and standalone mode, that time the power flow happens in only one direction. This one. So basically the power flow happens in one direction, and here in this case power flow is happens in both the direction. Excess power cannot be harvested in case if the battery is completely charged. Just once again I'll show that the system diagram, then it will be very easy. So this motor structure and the EV inverter structure, it is nothing but my basically a motor drive for the motor drive. Instead of that, I can put that three-phase connection again, rectify and connect it. This battery will come into the picture. Here the grid is connected and the PV is also connected in this system. So this motor structure, you can take it here, you can put one more DC to DC converter and connect it with the battery. That system is to be considered over here. So if you take it in that mode, the what kind of things will be there. So in case of excess power, already the battery is completely charged. You can't use that the excess power it is generated. That's what excess power harvesting is very, it's not possible. ROI is the return on investment, basically it is going to be very low. But in case of that exporting power to grid, it is going to be increased. So no additional income is generated, but here it's the income is going to be generated when we are pushing into that. The government policy is going to come up whenever that demand is more. Basically demand side, peak demand side, the amount of unit used for that, the cost, time cost variation. If you look at it, the peak demand, peak time, if you are consuming more power, then your the per unit charge is going to increase. At the same time, if you are supporting the grid through that exporting that the money part is going to be increase on the, such a possibility. So this is basically to make it the system to be in bidirectional. So the proposed configuration, we are doing it in this way. So the VSI1 is operated in a control, just I wanted to say, where you wanted to do that, the PV curve, if you see that we want to always operate it at maximum power condition. When the irradiance is present, it will operate it at the maximum power. Any of the algorithms, we can use it to make it the system to be operated at a maximum power. So the other control algorithm, if you see that the VDC power which we need to be maintained, here SVPWM is used and then the motor drive is going to be there. So if I talk about this is a onboard drive system, you can think of this even the four-wheeler or three-wheeler, the top of that three-wheeler or four-wheeler, it is covered with the PV panel. So it is an onboard charger. This particular topic is going to be with the onboard charger. So onboard charger means you think of it is a part of your system. So again, the optimization which I wanted to do, that's where we have gone to this particular configuration. Directly DC link bus, it is connected with the PV system. Here, actually, we need to connect the DC to DC converter. In case if we don't want to connect that, we can draw that the maximum power by operating either in this drive motor, which is basically electric drive motor, or it is pushing into the grid. So when it is going to be on side thing, what I'm trying to say is during the parking lot, when you are connecting, you can connect it with the grid. So the power generated, if the battery is completely charged, it can be pushed into the grid. In case if the battery is not charged, the power level is low, and the grid, it will take it from the grid as well as it will take it from the PV. During the night time, this PV system is not going to generate, but at the same time, based on the demand, the power will be flow from the DC capacitor to grid or grid to the DC capacitor, and it can be converted into that any of this motor system. So for that, during the daytime while running the system, the grid connected system will not come into the picture. So this particular system will not be used, and only the solar will be charging, and additionally to that the battery will be supporting the motor to control. Basically, the first control what we have done it in the controlled one is a space vector PWM base. The frequency reference is taken and 20 kilohertz one we have checked it. Similarly, the second stage of inverter is connected with the grid side converter. So how it is operating? Again, it is a simple space vector PWM we have used it, and we did the simulation for the different conditions when the irradiance is present, how the system is going. For the three-phase system, we can't use it with the 400 volts. We need a DC bus voltage of 800 volt. You can see here, it's basically a 800 volt 800 volt system has been presented over here, and the simulation, if you see that for the different irradiance values, so what are all the different irradiance values? Maximum irradiance is 1000 watts per meter squared, and then it has been gone to that 800 watts per meter squared, and I want to change it from that to 200 watt per meter squared. These changes, how it is impacting my power flow. So you can see that the grid current variation also, whether if the grid, the DC bus voltage is maintained constant, that means is basically we are trying to make it that the current battery voltage is constant. At the same time, the power flow variation, whenever the irradiance changes, according to that, the power level will also change. How it has been changed. So you can see here the current or in phase component. The current is in phase component, and this current is in a out of phase component. So at the same time, the speed of the machine where it is running it. So there is a no jerk when you change. But if you, in case of IC engine, when you change the gear, the variation in the speed you will be able to sense it. But in this kind of a motor based system, we will not be able to sense it. So basically what we have developed a particular system to show it. You can see here it is for that the power board is given at the bottom, and each and every control card is connected here. So basically it's a driver for that each bridge. So three cards are used for one bridge, another three cards are used for that. This is basically a control card. So we use, these are all the modules. You can see this is the power module. So it is not an intelligent power module. It is only a power module which IGBT back to back connected. The processor used over this particular case is a XMC 4400, and this driver, what we have used it, one ED driver. This one ED driver which will give that the basically a top and bottom drive, bottom driving pulses. The current continuous current, you can take it to 2 ampere, and peak current is around 8 ampere. But in case of microcontroller, whatever that the microcontroller we have used, it is a XMC. It is an automotive grade component. Basically, it is made out of Infineon processor. It works with a 200 megahertz, 200 megahertz oscillator, and that gives that the pulsar. So this basically this setup gives that the another advantage when we are looking at it as a PV based system. The PV which generates more, I am able to export it. The same time when we do all these things, we have to meet that grid code also. Basically, that I am talking about IEEE standard and UL standard. These two things is being taken care into the system, and it works according to that. So these are all the systems which makes the total system to be in stable operation in electrical point of view. So basically the chargers are not only doing it in battery charging, it can also act as a grid tie inverter. Because why we wanted to propose these kind of a things is basically when you make it the universal model for everything. The same board can be using of a electric vehicle battery. At the same time, the same module can be used for even if it is a solar water pumping application, even if it is a normal grid tie application, grid tie inverter, the same module need to be used. That is the main motto on this particular exercise, what we have done it on the system, which we wanted to make it as a one system, which will be making it as a common for all systems. So that is what we have done it with this particular one. So but makes these are all system which we whatever organization at the same time, it is not make sure that any of the last part. So when you look at it, these are all the aspects, these are all the systems where number of switches, number of components, what it is involved over here. It is also talks about the reliability problem. So we need to take it care of that reliability problem, and the bill of material cost is also we need to be taken care in this particular system. So if we look at it that the industry standard base components and the cost wise, it has to be meet. So that's why we have used it all the number of switches, whatever the number of switches are, even number of switches, only even number of switches. Why? Because that there's one leg half bridge modules are to be used to minimize the cost. So and also the easy repairability and replaceability. So we have done it this. So apart from this particular one, when we take it into the battery, we need to monitor that the battery health also into the system. So what we have to do is again sensing that the battery voltage and battery current, which I am talking about, that the number of cells and other things, different kind of batteries, where it has to be operated within the SOC, how it has to be taken. So those considerations, if you take it into constraint and put it into the constraint way, it will be another way of looking all aspects. So even though if the power flow is happening, we need to take care of the safety aspects too with the system. Okay, so that's it right now from my side about this things. If you have any queries, you can ask me. If you have any questions, you can ask me. Hello.
Yes, sir. Participants, if you have any questions, please. Sir, I think
Sorry for that thing is because I have to stuck up in some other things. Sorry for the background noise. Okay, so if you have anything, you can write to me bvperamal at gmail.com or bvperamal at nitk.edu.in. So I'll give the answers. Okay, thank you.
okay, sir. Thank you, sir. Thank you very much. Sir.
Yeah.
Sir, Muruganathan, sir.